In this video lecture, I will show another application of Maclaurin and Taylor series, and in particular, I will show how to solve differential equations with the power series. And of course, we're going to rely on some knowledge of some power series representations of some functions. And first, we'll do a simple differential equation just to introduce the technique, and then we'll do a somewhat not a trivial problem with the learned technique. So consider the initial value problem like this, and we do know what the answer is. It's a separable differential equation which we can easily solve. However, let's consider another approach. And in another approach, we're going to consider a function y, and we don't know what that function is, but let's say instead of the function itself, we will be looking for its power series representation around 0, because this is where initial value problem is stated. And what advantage do we get by considering the power series of this unknown function? Well, if we don't know what y is, then we don't know what the coefficients are, but we can express the derivative of this function easily using those unknown coefficients. So the derivative of y will be this. And we can write as many of these terms as we feel like, but let's just stop here. And what we're going to do next is we're going to restate the problem, but instead of y and y prime, we're going to use the power series. So we have a1, so the y prime is the derivative on the left hand side. And on the right side, we have y. But it is multiplied by 3. And we can simplify the left and the right hand sides. So the left hand side remains the same. But the right hand side is now 3a0 plus 3a1 x plus 3a2 x squared plus 3a3 x cubed, etc. And now we have two power series on the left and on the right. And in order for two power series to be the same at all values of x, the corresponding coefficients of x to some powers must be the same. So that means a1 must be the same as 3a0. So again, I'm looking at the free coefficient on the left, I'm looking at the free coefficient on the right. They must be the same. Then we're going to be looking at the coefficient of x on the left and then the coefficient of x on the right. So 2a2 must be equal to 3a1. Then we're going to look at the coefficient of x squared on the left and the coefficient of x squared on the right. So we have 3a3 must be equal to 3a2. And again, we can write as many of these equations as we have time for, but I'm just going to write 4. So 4a4 is equal to 3a3, and it kind of becomes like a system of equations, and it seems like we have more variables than equations, meaning we won't be able to find a solution, but we have an initial condition that we haven't used yet. So what does it mean that y of 0 is equal to 4? Well, that means actually a0 is equal to 4, because if you plug in 0 into this power series representation, all terms except the 0th one will be equal to 0, meaning the value of the function at 0 is the first coefficient. And with that, now we can kind of unwrap the whole series. So if a0 is equal to 4, that means a1 is equal to 12. Well, if a1 is equal to 12, then a2, remember we're gonna have to divide both sides by 2 there, so it's going to be 18, and then a3 will be equal to a2, and then a4 will be the 3 quarters of that, so it's going to be 3 times 18, 27 over 2, so it looks like 27 over 2. So again, we can write as many of these terms as we need. We're just going to have to consider more of them at the beginning. And finally, we can write the answer. It's going to be 4 plus 12x plus 18x squared plus 18x cubed plus 27 over 2x to the power 4, and so on. So we may not found the solution of this differential equation in explicit or in closed form, but we did find the power series representation of that solution, which has its own value. Alright, so this is the technique. It's pretty straightforward. Now let's try to do a problem which is not as obvious as the one that we just did. So let's solve this second order differential equation with 2 initial conditions. So if we let y to be a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the 4, etc., then y of 0. So I guess we're going to find the second derivative here first. So it's a1 plus 2a2x plus 3a3x squared plus 4a4x cubed, and we're going to find the second derivative here. So it's going to be 2a2 plus 6a3x plus 12a4x squared, etc. And maybe just to be safe, let's just add a couple more terms here. We have 5a5x to the 4, and we're going to have 20a to the 5x cubed, and we're going to have, this is 5 times 4, 6 times 5, so it's going to be 30a6x to the power 4. Now y of 0 equals to 1 means a0 is equal to 1, and y prime of 0 equals to 2 means a1 is equal to 2, because if you plug in 0 into here, everything but a1 will disappear, so a1 must be equal to the output of the function at 0. And now we're going to set up this equation. So we're going to take the y double prime. Just instead of rewriting it, I'm just going to take the copy of this. So this is my y double prime. And we're going to set it equal to 2xy. So again, I'm doing a little bit of algebra here, so I'm just bringing in this equation, I'm just bringing 2xy to the right. So the second derivative of y is equal to xy. So we're going to take the second derivative here. Actually, sorry, I should have taken the actual original function here. And multiplied it by 2x. So we're going to have 2x times a0 plus a1x plus a2x squared plus a3x cubed plus a4x to the power 4, etc. And we're going to simplify. So I'm going to have my second derivative right over here on the left, but on the right we're going to write this all out. So it's going to be 2a0x plus 2a1x squared plus 2a2x cubed plus 2a3x to the 4, etc. And now we're gonna set the coefficients of the corresponding axes equal to one another. Since there is no free coefficient on the right side, the 2a2 must be equal to 0. The coefficients of x produce this equation. The coefficients of x squared give us this equation. And the coefficient of x cubed will give us this equation. So we can write more of this if we need more, but let's just write these ones for now. And from here we'll learn that a2 is equal to 0, a3 is equal to 1/3 of a0, but since a0 is equal to 1, a3 is equal to 1/3. a4 will be equal to 1/6 of a1, and since a1 is equal to 2, a4 is equal to 1/3. a5 is equal to 1/10 of a2, but since a2 is equal to 0, a5 is also equal to 0. And we can continue this. However, let's just write what we have so far. And y as a power series can be represented in the following way. 1 plus 2x. Now we're missing the x squared term. Then we have 1/3 x cubed plus 1/3 x to the power 4. Then we have a missing fifth term, and then we continue with the 6th, 7th, and so on. So we didn't find the solution of this differential equation in closed form, but we did find the power series representation of the function that is a solution of this initial value problem. So what we have seen is an application of power series that allows us to solve some of the differential equations.